In this lesson, we're going to talk about a concept called Cavalieri's principle. Cavalieri was an Italian mathematician, and he came up with a pretty interesting concept for volumes. And it's based on the principle of parallel slices in the plane. So if I have two figures in the plane, so we're dealing with area, not volume, and at each height, their cross-sectional lengths are the same, then the regions, the figures, have to have the same area. So even if they're three different looking shapes, you have the center green leaf here, and over here it looks like the top's kind of stretched out a little bit, and over here it looks like it's both stretched out. We actually call this a shear, where it's like I take the top and I move it parallel to the bottom. Because all of the corresponding cross sections are the same length all the way across. If you measure here, it's kind of an optical illusion, but this length is the same as this length, which is the same as this length, and it's true for the entire shape, and they have the same height. Therefore, they're going to have the same area. It's like adding up the areas of all these little bitty lengths, and since they're all corresponding the same, they're going to have the same area. Well, if we think about volumes, there's a principle of that's called Cavalieri's principle that's very similar to what this parallel slices in the plane is all about. So Cavalieri's principle is this: given two solids that are included between two parallel planes, so the bases are parallel, if every plane parallel to those planes, so if every cross section has equal area and they have the same height, then the volumes of the two solids have to be equal. So the criteria is this: you need to have parallel bases, same height, oops, that's funny looking M, same height, and then same cross-sectional area. Those are the three things. If those three things are true, then the two objects have to have the same volume. So here's a few figures that kind of demonstrate this concept. In the first case, I have a rectangular prism, and this is a right prism. My base is A times B, and here's my height. And you know, with this vertical height, each cross section is going to be identical to the bases. Well, here's an oblique prism. Again, each cross section is identical to the base, A times B, and the oblique prism has a height of h. So it's like I took this guy and pushed him, scooched him sideways. The actual physical volume doesn't change. Or I can take him and bend him like a book. If you bend a paperback book, its volume still doesn't change, even though the sides are curved, because the parallel bases are still the same and the height's still the same. We could have two entirely different objects. And again, if they have parallel bases, and if they're at every level, their cross sections have the same area and they have the same height, then if you add up all the areas here, it's going to be the same as adding up all the areas there, and they're going to have the same cross section. Again, they can be completely different. So if these two have the same bases and the same height, and at every level the cross-sectional areas are the same, they're going to have the same volume. Same with this guy. Even though the steps look different, if at every level the area is the same, they're going to have the same volume. So the best way to demonstrate Cavalieri's principle is thinking of a stack of quarters. Okay, I got a stack of quarters. You know, and we're going to assume every quarter is identical. So we have parallel bases, and here's the height of this guy. If I just scoot the quarters, the height doesn't change, and we haven't lost any quarters, so they have to have the same volume. And again, here's why. You've got to, we have parallel bases, congruent cross sections, or each cross section has a congruent, they don't even have to be congruent cross sections. Parallel bases and cross sectional areas are congruent at every level. So cross sectional areas are congruent and congruent height. Those are the three conditions for Cavalieri's principle to work. If those three things are true, then the volumes are equal. Parallel bases. And at every level, the cross-sectional areas are congruent, and they have the same height. They got to have the same volume. So here's how we could apply Cavalieri's principle. A triangular prism has an isosceles right triangular base. So the triangular prism is going to look like this. Here's what one base looks like. Isosceles right means that these two sides are the same, and it has a hypotenuse of radical 32. And a prism height of 15. So the overall height is 15. A square prism has a height of 15, so now they have the same height, and its volume is equal to that of the triangular prism. So I want the dimensions of the square base. Well, Cavalieri's principle says if, and we can kind of use the reverse, if the bases were the same and they have the same height, and at every level the cross-sectional areas are going to be the same, then the volumes are going to be the same. Well, we know the volumes are the same, and we know they have the same height. And if you look at these, in a prism, every cross-sectional area is going to be congruent to every throughout the prism. So that means it's kind of the converse of Cavalieri's principle. Same volume, same height. We know that the cross-sectional area, no matter where you cut it, is going to be constant. Therefore, they got to have the same cross-sectional areas at the end. So once I find the area of this guy, I know he's going to be the same as the area of the square, and then I can work backwards to find the dimensions of the square base. So I'm going to label this side X and this guy Y. They don't necessarily have to be the same length, but they do have to have the same area. So let's find the length of these two sides and then the corresponding area. We know that x squared plus x squared is going to be radical 32 squared. So 2x squared is 32. X squared is going to be 16. So x is 4, which means the base area, it's a triangle, is 1/2 times 4 times 4, and that's going to be 8. So if this is 8, that means this is 8. So 8 over here, the area of a square is y squared is equal to 8. That means y, well, I can't write today, hold on. Let me do this again. Okay. Y squared is equal to the area, that's 8, which means y is equal to radical 8. We want this in simplest radical form, so each side length is 2 radical 2. So this is a case where we kind of use the converse of Cavalieri's principle. We know the volumes are the same, the heights are the same, therefore the base areas have to be the same. And we use that to work backwards to find the actual dimensions of each one. So now we're going to do some standard problems. This one we have an oblique hexagonal prism, and we want to find the volume of that guy. Well, we know that the volume is going to be the base area times the height. In this case, I'm given the base area is 17.3 square centimeters. The height is 6.4 centimeters. My units match. So this is a very straightforward problem. It's 17.3 times 6.4. And that's going to give me a volume of 110.72, and that's cubic centimeters. So if you're given the base area and the height, a volume calculation is pretty easy. Okay, and the second one, find the volume of an oblique circular cylinder that has a radius of 5 feet and a height of 3 feet. Round to the nearest tenth. All right, feet and feet, so my dimensions match. I know volume is going to be base area times height. In this case, the base area is pi times the radius squared. My radius is 5 times the height. So volume is going to be pi times 5 squared times 3. If I'm rounding to the nearest tenth, I get 235.6 cubic feet. Okay, this last problem is a bit more complicated, but it's still not bad. Prisms A and B have the same length and width, but different heights, so 4 by whatever and 4 by whatever. If the volume of prism B is 150 cubic inches greater than the volume of prism A, what's the length of each prism? So Cavalieri's principle does not apply in this case, because even though we have parallel bases and the areas would be the same, the heights are not. So they do share the same length, so I will label that length x, and we know the volume of prism A, we could say, is 4 times 7 times x, so that's 28x. And the volume of B is going to be 4 times 10 times x, so that's 40x. But now I need to come up with an equation so I can solve for x. I know the volume of prism B is 150 cubic inches greater than the volume of prism A. So the volume of prism B is going to be 150 plus the volume of prism A. So 40x is equal to 150 plus 28x. And that's a pretty easy equation to solve. If I subtract 28 from both sides, I get 12x is equal to 150. Divide by 12, and I end up with x is 12.5. And that's going to be inches. So that's just an example where you might have to set up an equation to solve at the end. And we'll do a lot more of these different types of problems in class.